Hello, my name is Sergey Ivanov, and I want to tell you about our recent work on homology of Lie algebras over commutative rings. This is a joint work with Fedor Pavutnitskiy, Vladislav, Romanovskii, and Anatolii Zaikovski. And the aim of this work is to show that there is no uniquely defined notion of homology of a Lie algebra over arbitrary commutative ring, and even over Z. If you work over fields, and if you have a Lie algebra over a field, then there is a very nice, well-defined notion of homology, and there are several equivalent definitions. But we show that these definitions are non-equivalent over arbitrary commutative rings, and we study relations between them, between different types of homology, prove that under certain conditions they are equivalent, they are naturally isomorphic, and provide some examples such that they are non-isomorphic. The topics of my talk are the following. First of all, I want to remind you equivalent definitions of group homology. I start from groups, not from Lie algebras. It's easier for me. And here I remind the language of relative homological algebra, the language of simplicial resolutions, and the language of Comonad derived functors. The second topic is 5 types of homology of Lie algebra. Here I define 5 different types of homology and explain you our main results. The next topic is about a spectral sequence that connects these different types of homology of Lie algebra. We call it Chevalley-Eilenberg spectral sequence, and it uses Puppy derived functors. And the last topic is Koszul complexes. It is in some sense additional topic, but it was very useful in our work, and I decided to add it here. Let me start from reminding you several equivalent definitions of group homology. Purely algebraic definitions. We don't consider topological definitions. We work only with purely algebraic definitions here. The simplest algebraic definition is given via Tor functor. It is just the Tor functor over the group ring of the trivial model with itself. This is homology of J with trivial coefficients. Here and everywhere in my talk, I will consider only homology with trivial coefficients. It is a very nice and simple definition. And there is a very similar definition, but it is given on the language of relative homological algebra. And let me remind you this language of relative homological algebra first. In relative homological algebra, we have 2 rings, R and S. S is subring of R. And the relative homological algebra is the homological algebra of R modulus, modular homological algebra of S modulus in some sense. In relative homological algebra, we replace all short exact sequences of R modulus by a smaller class of short exact sequences, by short exact sequences of R modulus that split over S. And we consider only such exact sequences. And instead of projective modulus, we consider a larger class of modulus that are called RS projective. They are modulus that behave like projective, but only with respect to such exact sequences, only with respect to S-split exact sequences. And we replace projective resolutions by RS projective S-split resolutions. They are resolutions whose components are RS projective. So they are from a larger class of modulus than the class of projective modulus. But this augmented resolution is not just an acyclic complex. It is more than acyclic. It is S contractible over S. So we use, instead of projective resolutions, we use these resolutions in relative homological algebra. And then RS relative Tor is defined similarly to the ordinary Tor, but instead of projective resolutions, we use this RS projective as split resolutions. And then we can consider this formula as a second definition of group homology. It is easy to check that this relative Tor relative with respect to the ring of integers coincides with the ordinary Tor, and then it gives the second definition of homology. It is not very interesting here because it gives the same answer. And generally, if R and M are projective over S, then the relative Tor coincides with the ordinary Tor. Here we have the group ring, which is 3 over Z, and Z, which is 3 over Z. So in this case, the ordinary Tor coincides with the relative Tor. Okay, let's go to the third definition. The third definition is given on the language of simplicial groups, non-abelian simplicial groups. It's a very different definition. And let me remind you the notion of pre-simplicial resolution. A pre-simplicial resolution of a group is a simplicial group, simplicial non-abelian group, that consists of three groups, components of three groups, and such that we can choose their bases so that they're closed with respect to degeneracy maps, and such that the zero homotopy group of this simplicial group is J, but other homotopy groups are trivial. This is simplicial resolution. If you like the language of model categories, then you can consider the category of simplicial groups as a model category, and then free simplicial resolution is just a cofibrant replacement of the constant simplicial group J. But we don't use the language of model categories in our work. If you have free simplicial resolutions, for any group there exists a free simplicial resolution, and then you can define a derived functor of any functor from the category of groups to the category of abelian groups, for example, as follows. You just apply object-wise this functor phi to this resolution, and then take homotopy groups. This is simplicial abelian group, and you can define its homotopy groups using the Dot-Kahn correspondence. You can think about these homotopy groups as about homology of the corresponding complex. This is a very nice definition of derived functors. It is independent on the choice of the resolution, so on and so on. Very nice definition. And if we take the simplest functor from the category of groups to the category of abelian groups, the functor of abelianization, then its derived functors are homology of a group homology, a functors of group homology shifted by one. It was proven by Quillen using the methods of model categories in his famous paper, Homotopy Algebra. And this isomorphism can be considered as the third equivalent definition of group homology. This is very nice definition, simplicial resolutions, and so on, but we prefer to work with, in some sense, standard resolution, with bar resolution. There is bar resolution for any group, and it comes from a Comonad on the category of groups. Let me remind you the general framework of Comonad derived functors. And this will be a particular case of Comonad derived functors. We prefer to use this language. Comonad derived functors are also known as Barbek derived functors, and they are defined by a comonad on the category C. For any such a comonad, where epsilon is a counit and delta is a multiplication, there is a simplicial functor whose components are powers of this comonad. And this simplicial functor is known as bar construction of J. These degeneracy maps and phase maps are defined using epsilon and delta for unit and for multiplication. And then for any object of C, we have a simplicial object in C, which is, one can call it bar resolution of this object. And then for any functor from this category C to any abelian category, we can define its derived functors with respect to this comonad as follows. We just need to take this bar construction, apply it to this object, then apply phi to this simplicial object, and then take homotopy groups. And again, here homotopy groups are defined using the Dolphin correspondence. So these are homology groups of the corresponding complex, chain complex. And we will work with this comonad derived functors. On the category of groups, we have a natural comonad that comes from the free forgetful adjunction. From the category of groups to the category of sets, we have a forgetful functor. From the category of sets to the category of groups, we have a functor of free group. They are adjoint, and this adjunction gives a comonad on the category of groups. And the corresponding bar construction gives a free simplicial resolution. So using this, we see that we can define homology, group homology, as derived functors of the functor of abelianization with respect to this comonad. And this we will prefer this definition. This is a second version of our third definition of homology, and we will use this one in the case of Lie algebras. Okay, let's go to Lie algebras. First, I want to discuss a little bit Lie algebras over fields. For Lie algebras, we can also give these three similar definitions of homology, and they will be equivalent. It's not difficult to check it. And there is another one. There is one more important definition in the case of Lie algebras. It is given via Chevalley-Eilenberg complex. For any Lie algebra over a field K, there is a complex that we denote like this, whose components are exterior powers of J of the Lie algebra, and with some explicit formulas for the differential. For example, this map is the commutator map. And then homology of Lie algebra is amorphic to homology of this complex. This is one more. This isomorphism can be considered as one more equivalent definition of homology. This definition is very important because this complex is very small and convenient. For example, if your Lie algebra is finite dimensional over your field, then this complex is finite. Even if your Lie algebra is not finite dimensional, this complex is convenient because you don't need to work with the universal enveloping algebra of your Lie algebra. You work only with the Lie algebra itself and its exterior powers. So it's very convenient. Okay, now let me define you our five types of homology of Lie algebra. First, the simplest one is Tor homology. We define it as Tor functor over the universal enveloping algebra of the trivial module with itself. here I assume that K is a commutative ring and J is a Lie algebra over K. The second definition is given on the language of relative homological algebra. It is a relative Tor homology, which is denoted like this with RT here. It is just relative Tor over the universal enveloping algebra relative to the base ring K. Here they don't necessarily coincide because this universal enveloping algebra is not necessarily projective over K. The next definition is Chevalley-Eilenberg homology. They denote like this, H. They're defined using the Chevalley-Eilenberg complex. Homology of the Chevalley-Eilenberg complex. The next definition, simplicial homology. Simplicial homology is defined as Comonad derived functor of the functor of abelianization with respect to Comonad that comes from the free forgetful adjunction of the category of Lie algebras with the category of sets. We have a forgetful functor from the category of free algebras to the category of sets, and we have functor of free Lie algebra from the category of sets to the category of Lie algebras. This gives us Comonad here. But there is another forgetful functor from the category of Lie algebras, not to the category of sets, but to the category of modules. And we define relative simplicial homology similarly to simplicial homology, but here we consider another Comonad. We consider forgetful functor from the category of Lie algebras to the category of modules, and the functor of free Lie algebra from the category of modules to the category of Lie algebras. This gives another Comonad from the category of Lie algebras. And we define relative simplicial homology as derived functors over this with respect to this Comonad of the functor of abelianization. Okay. Now I want to show you a very simple example that shows that not all of these definitions are equivalent. If you take, if you consider Lie algebras over Z and take the Lie algebra Z mod 2 with trivial structure of Lie algebra as abelian Lie algebra, then it's very easy to compute that the third Chevalley-Eilenberg homology of J is trivial, but the third Tor homology is not trivial. It's Z mod 2. So this very simple example shows that at least not all of these definitions are equivalent. However, we prove the following positive results. We prove that if K is an arbitrary commutative ring and J is Lie algebra over K, which is flat as a module of a K, then all these types of homology are naturally isomorphic. And another positive result that we prove is the following. If K is a principal ideal domain and J is arbitrary Lie algebra, then the following three definitions, the following three types of homology are naturally isomorphic. Chevalley-Eilenberg homology, relative Tor homology, and relative simplicial homology. Naturally isomorphic. In some sense, they are relative types of homology. Them like this. And moreover, all types of the second homology are isomorphic over principal ideal domains. And moreover, they can be computed using the Hopf formula. If you present your Lie algebra as a quotient of a free algebra by some ideal R, then you can compute the second homology using this formula. Okay, these are our positive results. But we prove the following non-isomorphisms. I mean that there exist a Lie algebra. For example, this non-isomorphism means that there exists a Lie algebra such that these guys are non-isomorphic, and we prove that almost all of them are non-isomorphic. The only thing that we can't prove is that relative simplicial homology and relative Tor homology are non-isomorphic. For all other types, for all other couples of homology, we can prove that they're non-isomorphic. We can give an example of K and J such that they're non-isomorphic. And for principal ideal domains, as I already said, we prove that these three types of homology are isomorphic: Chevalley-Eilenberg, relative simplicial, and relative Tor homology are isomorphic. But all other couples are non-isomorphic. All other guys are different. In particular, we provide the following some example of a Lie algebra over Z, such that its third simplicial homology is isomorphic to direct sum of countable copies of Z mod 2. Its fourth homology is isomorphic of to the direct sum of 4 copies of Z2, and all other third homologies, all other types of the third homology are trivial. This is the most interesting example because it's over Z. First of all, we are interested in the algebras over Z. We also construct examples of a more complicated commutative rings. We construct a commutative ring K and the Lie algebra over these commutative rings such that we have the following non-isomorphism and another example of commutative ring and another example of a Lie algebra such that we have the following non-isomorphism. These examples show that only possibility for isomorphism among these 5 types of homology is an isomorphism between relative Tor homology and relative simplicial homology. And we can't prove this, but we believe that there is no such an isomorphism, and we leave it here as a conjecture. We believe that there exists a commutative ring such that the functors of relative Tor and relative simplicial homology are non-isomorphic. We also study some connections between these different types of homology, and we constructed a Chevalley-Eilenberg spectral sequence, a spectral sequence that we call Chevalley-Eilenberg spectral sequence. It was motivated by our counterexamples, by our main example. The most complicated part in this example of a Z was to work with simplicial homology. It is difficult to compute it. And in order to work with this, we constructed a spectral sequence that we call Chevalley-Eilenberg spectral sequence. In this construction, we use the notion of Dolpuppi derived functors, Dolpuppi non-shifted derived functors. If you don't know this notion, then I can say you that the non-shifted derived functors, in the sense of Dolpuppi of non-additive functors, from the category of modulus to the category of modulus, can be defined using Comonad derived functors. It is just Comonad derived functors with respect to the free forgetful Comonad on the category of modules and on the category of modules. We have a free forgetful adjunction between the category of sets and the category of modules. This gives us a Comonad on the category of modules. And we can consider derived functors with respect to these comodules, and they are just Dolpuppi non-shifted derived functors. Okay. The Chevalley-Eilenberg complex induces, in some sense, Derived versions. It's derived versions. We can consider derived versions of the Chevalley-Eilenberg complex that we denote like this. Here, lambda n is considered as a functor from the category of modules to itself. It is a functor of exterior power. And we take its derived functors in the sense of Dold-Puppe and apply them to the Lie algebra, consider it as a module over K, and only these differentials depend on the structure of Lie algebra here. Then homology of these complexes are denoted like this. Chevalley-Eilenberg homology with indices n and m. If m equals to 0, then it is just the Chevalley-Eilenberg homology. For other m, it's a new invariant of a Lie algebra that we call derived Chevalley-Eilenberg homology. We prove that there is a spectral sequence converging from this derived Chevalley-Eilenberg homologies to Simplicial homologies. And using this spectral sequence, we show that there is an exact sequence, the following exact sequence for any commutative ring and any Lie algebra over this commutative ring. There is an exact sequence. We're interested in this third Simplicial homology. Here we have Chevalley-Eilenberg homology, and here we have Chevalley-Eilenberg homology, and here we have derived Chevalley-Eilenberg homology. And this exact sequence helps us to reduce computations of the third Simplicial homology to computations of this guy, Chevalley-Eilenberg homology with indices 2, 1. This Chevalley-Eilenberg homology with indices 2, 1, more or less by definition, is the co-kernel of some map between the first derived functor of the exterior cube of J and the first derived functor of the exterior square of J. I want to tell you, I want to give you some explicit description of that. We found some explicit description of this functor on the language developed by Brin and Jan. Brin and Jan, in their papers, gave some more or less explicit descriptions of these Dold-Puppe derived functors of exterior powers. And we use their description to give a description of this guy. Following them, we denote by omega the first derived functor of the exterior square. And we show that there is an exact sequence, the following exact sequence with some explicit description of phi there on the language of Brin and Jan. And using this, we can compute this guy for some concrete examples and show that they are counterexamples. Show that the third homology, the third Simplicial homology, is non-isomorphic to the Tor homology and other homologies. Okay, now I want to tell you about my additional topic, Koszul complexes. Koszul complexes. This topic just about commutative algebra, which was very important for us, which is very useful in our proofs, and we prove some results about these Koszul complexes. Let me tell you about them. In commutative algebras, there is a very general notion of Koszul complex. If you have a commutative ring R and a module E, then for any homomorphism from E to R, there is a very explicit complex, which is called Koszul complex of F. Full differentials are defined by some explicit formulas and depend on f. For example, this differential is just f. If we take an arbitrary module over some commutative ring K, we can consider its symmetric algebra. And we take the symmetric algebra as the base ring for this construction. And as E, we take this symmetric algebra tensor by M. And we take the homomorphism of multiplication from here to here. Then this construction of Koszul complex in this case gives us this general construction gives us the following complex. This exterior powers over R over the symmetric algebra can be described as follows: as the symmetric algebra tensor with the exterior powers over the base ring K here, and we obtain the following complex. But it's not just a complex, it is a graded complex. There is an additional grading here that comes from the grading of the symmetric algebra. The complex has natural gradings, and its components are the following. The complexes of length n, and the nth component starts from the exterior power of m. The last term here is the symmetric power of m, and in the middle we have tensor products of symmetric powers and exterior powers. When n equals to 2, we have the following complex, for example. The following very short complex. And we call this complex Koszul complex also. Koszul complexes. Okay. It was known that these Koszul complexes, consisting of symmetric and exterior powers, are acyclic for flat modules. But we prove a more stronger result about their exactness. We prove the following. Assume that one of the following properties hold. Either K is a principal ideal domain, or M is flat, or N is invertible in K. Then in this case, this complex is acyclic. And it is not just acyclic, it is pure acyclic. Pure acyclic means that if we tensor this complex on some other module, then it will be acyclic. It will be also acyclic. And moreover, in the case 3, it is contractible. However, on the other hand, for each n, we provide an example of a commutative ring K and a module M such that this first map here is not injective. So this theorem doesn't hold for arbitrary commutative ring and arbitrary module. This is what I wanted to say to you. Thank you for your attention.